Welcome back to my channel. Today our topic will be Rust algorithms and data structures. Now, first of all, to all my Muslim viewers, Ramadan Mubarak, تقبل الله منا ومنكم صيامنا وصالح أعمالنا, and I wish you a holy and blessed month. And yeah, let's see the course, what's it all about. So who is this course for? This course is aimed at programmers who are new to Rust, who knew some of the fundamentals and the syntax but want to dive in a little deeper, and for web developers coming from a JavaScript or TypeScript background. This course is suited for you because the exercises in the original were for JavaScript. So maybe you have even solved the original exercises. I will show you in a minute. But yeah. And lastly, for curious people about system programming or system programmers who are looking for an alternative to C and C++. So, this is the original course I've talked about. It's from FreeCodeCamp, really an excellent course for people diving into web development, and it's called JavaScript Algorithms and Data Structures. Now, what I've basically done is I've taken these exercises and translated them to Rust. So this is now the Rust Algorithms and Data Structures course. Welcome. So as you can see, this is the site on FreeCodeCamp. We are only concentrating on the intermediate algorithm scripting because the other stuff is pretty basic. And yeah, as you can see, we have here the exercises 21, and if I go to my GitHub over here, and I can then run cargo run, and as you can see, we have the same exercises over here. Sum all numbers, diff to arrays, seek and destroy. It's the same, but as I've said, this is in JavaScript, this is in Rust. So as you can see on FreeCodeCamp, of course, you have a nice UI. In my course, it's terminal based, but I guess this wouldn't be a problem. People interested in Rust. So I can go into the folder, I go to source, then as you can see we have here exercises. These are my solutions. You can put your own solutions if you want to. See the exercises, and as you can see you have all the exercises. So we can then start with sum all numbers in range. So sum all numbers in range, like that. And as you can see, we open the file over here, and these are the tests. I have written here 4 tests. Here I guess there are 5, but I think 3 to 4 tests are sufficient. And yeah, I've basically also made sure that, for example, the function name stays the same, the arguments have the same name, just for consistency reasons. Okay, and I will just show you how you can get the program. So if I go into my downloads folder over here, and I will then go to my GitHub. As you can see, you have here Rust algorithms. By the way, this is my GitHub page. I will put the link in the description. Rust algorithms, and then you can just grab here. You can git clone, like that. And as you can see, we have in a folder Rust algorithms. So cd into that. And then you can run cargo run, and you are, of course, it will download some of the packages it will need. This is just slow for the first time. Just make sure that you are working with the same tools. For example, regex, I've used my solutions. And yeah. And then when it's finished, you can then run cargo run as we did over here, cargo run. As you can see, we then get all the exercises, and then, for example, I can make this a little bit bigger. As you can see, we are over here, and then, for example, exercise number 1, I can press here 1, and then it will give me the results of the tests. It will test. As you saw, we have in the first exercise 4 tests, and now everything had failed. So this is how you can check. If you want to check every test from every exercise, you can press all. And of course, we didn't implement any exercises, so every single one of them failed. So there are 82 tests in total. All right. And before we dive into the exercises, I want to give a brief introduction. Why Rust? Why are we even bothering with type annotations, lifetimes, generics, all this additional syntax? And let's see, for example, this programming languages iceberg. So you have here the entry-level languages, for example, Scratch and Basic. Scratch is a tool of MIT, and it's basically working with shapes and colors and forms, stuff like that. So you get the concepts of programming. And I guess Basic is just what Scratch is today to people in the 80s and 90s. So most of them probably the first language they touched was Basic. Then the tip of the iceberg is scripting languages. So over here we have, of course, JavaScript, the most popular one, Python. We have, for example, SQL. It's also very widely used for database administration. We have PHP, Ruby, Lua, Julia, PowerShell, Bash. Of course, if you use Linux, you're always confronted with Bash and Bash scripting. So these are the scripting languages. Then over here we go more into the commercial domain. So as you can see, we have Java, we have Kotlin, Swift, C#, TypeScript, Go. These are statically typed compiled languages. Then over here you have functional languages, not so popular anymore, I guess, but of course Haskell, this I know very well, Scala, and right next to that is, or right below to that is systems programming languages. For example, C, C++, and Rust. So in terms of power and versatility, Rust is on the same level as C and C++. And these languages give you powerful tools, which basically you don't have with these languages. Especially in C, for example, you can have pointers, you can manipulate values in memory, and C basically all the operating system, Windows, Mac, Linux, they are built on C. So very powerful language, and of course Rust and C++ are on the same level. Now Rust gives you some tools, and C++ too, which in C you would have to build yourself. For example, a linked list or hash maps, hash tables. You will have to build that in C yourself, while in C++ and Rust they are given to you, so you don't have to implement it once again and reinvent the wheel. Well, next to that we have high performance languages. These are languages for very specific cases, for example, databases, search engines, probably game engines. These are languages for very specific use cases. Then we have branch-specific languages. For example, we have here COBOL, which is a very, very old language, like the dinosaur of all the languages over here. And COBOL is still used today, especially in banking systems. And you know, you have here banking system, you have finance, you have science, which deals with very large numbers and very small numbers at the same time. So these are very specific languages, probably or mainly used for heavy computation. Now over here I have some esoteric languages. I really don't know a lot of them. I know BrainFuck because BrainFuck was developed by a Swiss physics student, and basically what he wanted to show is if it's possible to build a language with the smallest possible compiler, and his compiler, I guess, was around 170 bytes of C code. So this is really impressive what he accomplished there. And of course, Holy C is the language of the Temple OS operating system by Terry Davis, an exceptionally talented programmer, which had a bad fate. And of course, in the end, low level. So here we are really at low level stuff. Punch cards, not that much used anymore actually. x86, this is assembly code, pretty low level. And we have here transistors, logic gates. I guess this should represent kernel commands, and that maybe an electron. Of course, these are more hardware related. We are especially focusing on software. We don't bother about hardware as programmers because we don't have to. It's not our domain. But we will take a look at assembly, of course, because assembly is still on the software side. And there is a little bit of clash between people, and some of the people refer to C or Rust or C++ as low-level languages, and some of them say no, these are still high-level languages. So I guess this is a matter of perspective. So if you're coming from a JavaScript and Python background, C and Rust and C++, they might seem pretty low level because you're dealing with memory, you have to deal with pointers and stuff like that, you know, really low level stuff that you don't have to worry in these high level languages because it's all done for you automatically. And of course, if you're coming from an assembly background, you would say, yeah, these are high level languages because they abstract away a lot of stuff that is happening in the processor, in the CPU, which are not represented. This is just an abstract representation of what will then be translated to assembly code. So my bet on that is I would refer to them as mid-level languages because they are kind of in the middle. You know, here we have the high-level ones, here we have the really low level, and I guess mid-level languages is a good term for these languages. So maybe just to go step by step, why we are even bothering learning this when we have this over here. And let's start with the UI. So a UI, a user interface, gives the user an interface they can interact with without writing code or actually even caring about what the computer does internally. So for example, we have here Microsoft Word, which is a pretty popular program, and as you can see, it's working with symbols and text, and it has nice graphical user interface. And yeah, so as you can see, for example, if I mark this text and press over here, the text will get bold. So this is probably common sense to us because we have grown up using computers, and you don't even have to think about it anymore. It's just common sense, it's natural to you. So you put your pointer here, you press this, the text will get cursive. So this just happens all internally. So a UI basically abstracts away all the code, all the functions, everything that's happening inside the computer, just for the user to have a nice experience. Because let's be honest, most computer users today, they probably will never write a single line of code. That's okay, you know, not everyone is a programmer. So for example, over here we have the Google homepage, and very basic, you have a text box and two buttons over here. Again, feels natural. You just type, you give an input, you type over here your search query and press the button, and it's all done for you. Same thing on mobile. As you can see, Instagram, for example, you press over here, it will open the story of this person. You press 2 times on the picture, you will then give a like to this picture. So user interfaces or graphical user interfaces work a lot with shapes and symbols and colors, just to make it easier for the user. Now, just to show you a little example, I have built a small very small website. Click me, and you can open index.html. As you can see, we have here a pretty huge button. Now if I click this button, what will happen? It will give out an alert, you clicked the button. Pretty simple, just so you understand the concept. Now, if we look at the code behind this button, as you can see, this is an HTML file, and every web page basically uses HTML. So here is our button. Button, click me button. So in HTML we close every tag. And this button doesn't do anything. You will have to give it functionality, and this functionality you can give by using a programming, or in this case a scripting language. Now in the web, in the browser, most of scripts are actually written in JavaScript. So as you can see, we have here 2 script tags, and all we do here is we are storing this button, or grabbing the button, putting in inside variable, and then to this variable we can add an event listener. If we click on the button, this info function will get invoked, and then all this function does is just it will give out an alert, you click the button. So as you can see, simple button, but if we look under the hood, you can see there is actually code implementation, which is abstracted away. So let's see, JavaScript is not a compiled but an interpreted language. It's dynamically typed and there are no type annotations necessary. The big problem with JavaScript really is that errors could happen at runtime when you don't even know. So you have a running program which has customers who use it and then it crashes at runtime. This is pretty bad. So to give you an example, we have here a JavaScript function make upper which takes one argument. Now all this does is it will take this argument s and will put it to uppercase like that, and then it will return this string that was put to uppercase. Now when we call the function with the argument test, this is a string, and we log it out, then I can write the command node upper.js, and as you can see, as a console output we will have test but in uppercase, basically what this function did for us. Now this is all working pretty well, but the problem over here is that s really could be anything. So what if I would pass this function an integer instead of a string? Now as you can see, we will get a type error. S to uppercase is not a function. The problem right here is that when I save this file, it's saved. You know, you won't get any error. You maybe think it's working fine, but if you're dealing with user input especially, you don't know. Sometimes the user puts out stuff that you don't accept, and this would be really bad because it would crash the server. Now to work around this, it would be possible to put a guard over here. So just checking if type of s is equal to string, then we return the argument to uppercase, and if it is not a string, then the argument s should be a string. So we have made this function a little bit safer, but still, you know, this you have to do in every single function, and this, I can tell you, gets boring and tedious very quickly. So Microsoft came up with TypeScript, and TypeScript is a superset of JavaScript, and what TypeScript does is it basically emulates JavaScript as a compiled language, where the compilation target is JavaScript. So JavaScript is an interpreted language, as we've seen, but TypeScript makes it act like a compiled language. It's still interpreted, but TypeScript makes it act and behave like a compiled language. It's basically an illusion. So with TypeScript you have basically JavaScript, but strongly typed with interfaces, generics, and all the good stuff from modern languages. Again, here is a picture just to show you. As you can see, we have here JavaScript, and TypeScript is the superset. So if you have a TypeScript file and you write only JavaScript in it, it's a perfectly valid TypeScript file too. Now again, TypeScript has then to be compiled to JavaScript. So JavaScript is the compilation target of the TypeScript compiler. Why? Because the browser doesn't run TypeScript. It doesn't know TypeScript. It also doesn't worry about it. JavaScript is the language that the browser understands, so we have to compile our TypeScript code to JavaScript. As you can see, same function, but this time in TypeScript. And as you can see, we have gotten rid of this guard if s is equal to string, but we can now use type annotations. So we here define that the s parameter has to be of type string, and the return type of this function has to be of type string. So if we pass it a string, then the string will get uppercased, and as you can see in the terminal over here, I guess you have noticed it, we have an additional step. So compiled languages have to be compiled before they can be run. So we compile using TSC, TypeScript compiler. We put this upper.ts as an argument, and then we can run the output, which is the upper.js file. And what it will give us is test, but uppercased. Now, let's again try to call this function with an integer. And as you can see, the editor will then automatically give out this error. Argument of type number is not assignable to parameter of type string. So this is actually the very nice thing about strongly and statically typed languages. The compiler will check for you if this is actually possible or not. So we said we want here that s is a string. If we pass it an integer, it gives us an error. Now again, if we compile upper.ts in this state, it won't even compile. So we just have to fix the bugs and errors in the program, and then we can compile it. And this might seem a little bit like an overhead, little bit of extra work, but in the long run, you will save yourself a lot of trouble and headache. So this is basically the purpose of compiled languages. And as you can see, just really quick, here is the directory, and we have the upper.ts. When we run tsc upper.ts, we get as output the upper.js file. Now, if we look into the upper.js file, then as you can see, it's once again just JavaScript, because the browser needs JavaScript. It can't handle TypeScript files. So we are back at JavaScript. Now, maybe just to show you a little quote which gives a little insight of what's happening over here. Every program is a set of instructions, whether it's to add two numbers or send a request over the internet. Compilers and interpreters take human readable code and convert it to computer readable machine code. Now, your browser has to convert the JavaScript to machine code, because your computer doesn't understand JavaScript, and it doesn't understand C or Python or Rust or really any language. It doesn't understand it. It understands zeros and ones, bits and bytes. So, as we've seen, JavaScript is an interpreted language. What that means is that, for example, in your browser, in Chrome, you have the V8 engine, which is an interpreter. Now, this interpreter is written in C++. So, as you can see, we don't write the interpreter in JavaScript just because C++ is faster than JavaScript. So this interpreter will take the JavaScript file or the JavaScript code, and it will translate line by line by line to machine code. First line, machine code. Second line, machine code. Third line, machine code. So it translates instantaneously to machine code. Like, for example, if you watched the news and there is a guy who speaks a foreign language and there is a translator which instantaneously translates all he says. You can imagine the V8 engine or the interpreter doing the same. He takes JavaScript code and line by line interprets the machine code. So it translates from that to that. Same thing with Python. Python is also an interpreted language. So the interpreter is called CPython, simply because it's written in C. Why? Because C is faster than Python, because it's a compiled language. And again, it will take line by line and execute every line, translates every line and executes it. So, little summary on interpreted languages. Interpreted languages, or the code of interpreted languages, get translated or interpreted line by line and translated to bytecode or machine code directly. This makes it a lot slower than compiled languages, because you have to imagine that in compiled languages all this stuff is happening in advance. So when you run the program, you run the binaries. You don't run an interpreter. So, third point, errors and bugs may be in the program which will be found only at runtime. So if you have a JavaScript file, you can save it and load it up to the internet on an FTP server, for example, and you won't notice if there are errors, and you just hope that there aren't errors, and if there are errors, that there are not errors that will crash the whole server. So, and often offer dynamic typing and smaller program size, so that's a benefit of interpreted languages. They're smaller and they are platform independent. Now let's have a look at compiled languages. So for example, C is a compiled language, which means that the C code will be put into a compiler. So the C code will get compiled to assembly code. In this case, for example, x86. And then from assembly code, it will get assembled to machine code. Now, this, of course, is a lot faster because, as I've said, this all is happening in advance. So you then get the binary and you can distribute the binary to your customers, to other people, and they just can run the binary. Now, let's see actually how this is happening. So from C to assembly to machine code. So we have over here this C code. We declare some variables f, g, h, I, j. And then we say that in the variable f, we want to store the result of these operations. Now we want to add g plus h and I plus j, and then subtract this result from this result and then store it into f. Now, as we've said, this is an abstraction over what is actually happening in the CPU, because this C code will then get compiled to this assembly code. So I've taken the MIPS assembly this time because I'm not familiar with x86, but I know some of MIPS assembly. So as you can see, we are here working with registers. Now registers are in your CPU, and they're actually physical registers which store data. So as you can see, we don't deal with abstract models over here. We deal with real physical stuff in the CPU. So what we have over here, just really quickly, G plus H, we have the register S1 plus S2, and we will store the result in S0. Now the second thing, I plus J, will be S3 plus S4, and we store it inside S1 register. And then in the end, we just subtract this one from that one. So we subtract this S1, the result of this instruction over here, and we subtract it from S0, which is the result of this instruction over here, and we store the end result in register S0. So this is actually what the CPU will do. This is exactly the instructions for the CPU. Now again, this is also a human readable representation, so you can't feed that into your CPU, because as you can see, we have here ASCII characters. We have an A and a D and a D. The computer doesn't know how to read that. He doesn't deal with ASCII characters or numbers or this dollar sign. He doesn't know. So this is a human readable representation of actual machine code. So an assembler will then translate this assembly code to machine code, and this will then get fed into the CPU, and the CPU will know how to read that. But as you can see, C 2 lines of code, assembly 3 lines of code, binary 3 lines of code. So this is the equivalent. This assembly is the equivalent of the machine language, but in a human readable format. Now if you're coding in assembly, of course it depends on the processor architecture. So you have x86, you have ARM and various others, and these slightly vary. Alright, so why compiled? Just because they are a lot faster than non-compiled programming languages. As you can see over here, time, the fastest language of course is and will remain C, because it's just a really small language. Then you have Rust on the second place, even before C++, which has surprised me, to be honest. And you have C++. So these three languages are, of all the languages, the fastest to execute. This is simply because they are compiled, and we will see other reasons for that. But yeah, again, summary: compiled languages, they are the fastest languages. If there are errors and bugs related to the language, the program just won't compile. So the compiler will complain. You have to fix that before I will compile this code. And third point, program has to be compiled again if there are changes. So that's a little downside. Anytime you change something in the program, you have to recompile the program. As we've seen, for example, with TypeScript, when we made a little change, we have to recompile the program. Alright, now we have seen these languages: Java, C#, TypeScript, Go, Haskell. So you might ask, okay, I understand these are slower and they don't have types, so these have types and they are compiled, so why we don't use these languages? And in fact, many people do, and it's nothing wrong using this language. I just try to make the point why it's even worth the learning and all the power and energy you put into learning these languages. So there are, of course, benefits, you know, otherwise no one will deal with it. So why not just using these? So these actually are a little bit better than these, for example, in a commercial domain, but still they have one simple problem, which is called garbage collector. So a garbage collector manages the allocation and release of memory automatically. And you can imagine garbage collector is like a program that runs inside your program. So it's another program inside. The garbage collector slows down programs as it has to regularly check if variables are still used and drop them or free them in memory if not. And Rust does not have a garbage collector, so memory has to be managed manually. Now again, a garbage collector just looks, for example, if you have here a Java program and you declare a variable called name. Now you will use the program, but there will be a period of time in the program probably that you won't use this variable anymore. Now this would be a waste of memory, and with time the program uses a lot of memory if no one comes and cleans up the memory which is not needed anymore. So this is the task of the garbage collector. He will just from time to time check the program and see, is this variable still used? If it's not, then the memory location which is holding that value in memory will get freed or cleaned up. And of course this also takes time because the garbage collector has to look inside your program and find out. And this, of course, will add overhead over your program. So Rust does it a little bit differently. In Rust there are scopes like in many languages, and for example in this main scope we declare a string hello inside the variable s. So s comes in scope or into scope on this line number 2, and then we pass s to this function, takes ownership. So Rust has a model of borrowing and ownership. This variable over here, s, will get passed over here, so this will get moved out. S values moves into the function and is no longer valid here. So over here we can't use s anymore because it has moved over here. Then we print out the string, and as s over here, some string, is then in this scope, it will get freed over here. Here some string goes out of scope and drop is called. So this will get dropped and is not available anymore. Other thing with integers, so x is an i32 integers because that's the default type of integers in Rust, and then we pass this to makes copy. So because this is an integer, it will not actually move this variable, but it will make a copy of this variable. And so this is just a copy, this argument, some integer, and here some integer will get dropped. But in the main program, in this scope, we can still use x because we just passed a copy of x. This is just really an overview. I suggest to you, if you have trouble understanding the concept of borrowing and ownership and borrowing, you can watch my Rustlings lectures, and I will explain in great detail how this works, or you can watch other videos, because in this course I won't get into the details. I just want to give you an abstract overview and why we are using that. So as you can see, we have reached over here system programming language, and you might now ask, okay, I understand why we prefer that over this or over this, but why not just using C or C++? They're around for decades and they've proven that they're really capable of building great things with these languages. For example, C, as I've said, every operating system is built on top of C. So why not using these? Why we need another language? So why not just using C or C++? And the main reason for that is memory safety. So Rust is a memory safe programming language. There are no raw pointers in Rust like you would have in C and C++. I have to say in safe Rust because there is an option to use actual pointers, but this is called unsafe Rust, and we won't cover this in this course. There are no segmentation faults, so anyone dealing with C and C++ knows exactly what I'm talking about and how annoying this is. And this means basically just accessing memory locations we are not actually allowed to access. And we have no Daniel pointers due to lifetimes. We have no null pointer dereference. And the model of ownership and borrowing keeps Rust programs safe. So it's really about memory safety. So just to show you some examples of segmentation faults, for example, writing to read-only memory. So we have over here a string, hello world. We now want to access the first character, and in C, as you know probably, that a string is just an array of characters. That's why here it's called char, and this is just a pointer to the first letter inside this array. So we try to access this by using the reference operator and putting this age character. Now, of course, this will give us a segmentation fault because we attempt to write to read-only memory. Here we have another very, very famous example of null pointer dereference. So this is one of the most common mistakes in C and C++. You have a null pointer, basically pointer which points to no value at all. And then you try to access this pointer. So in here we try to print out the address of the pointer and the value of the pointer. Again, this will result in a segmentation fault just because it doesn't point to anywhere. So it can give us access to a location we try or we attempt to access. Next, buffer overflow. So over here, as you can see, we have a string, and as I've said, a string is basically an array of characters, and then we are looping from 0 to 19. Now the problem is this string, including the null terminator, is just 12 characters long. So we exceed here the boundaries of this string. Now we try to print every value from here, and as you can see, again, C is a compiled language, so we have to use here GCC, the GNU C compiler, to get an executable. And as you can see, we are printing out hello world. Looks pretty fine. But as soon as we start to go over the boundaries, we have these weird symbols. And this is happening because we are accessing memory beyond the memory in this string or character array. And this could lead to very dangerous situations. So many systems have been hacked or breached because of buffer overflow, because, you know, I just have now printed some additional characters, but if you have access to a lot of memory, then you can basically read what is stored in memory of that person's computer. And this is very dangerous, and it happened a lot. It still happens a lot. And the last example is Stack Overflow. This happens, for example, you have a recursive function and you don't have a base case, so you just are stuck in an infinite loop. And as you can see, inside main we call main. So this is the schoolbook example of an infinite loop. And again, we compile the program, we run it, and we get segmentation fault. So, quick summary, why Rust? It's a fast compiled language with helpful compiler messages. So the compiler is really helpful and helps you along the way. And it's strongly statically typed language. There is no garbage collector for fast execution time, so your program will run a lot faster without the garbage collector. There is memory safety in place, and you have modern syntax. Alright, this was the presentation. Now let's dive into the actual exercises. So I will close that over here. Let me push that over there, like that. And I just will show you really quick if I go to course code, I have prepared something for you, just so you saw it on an actual machine, because you have seen a lot of abstractions now, and if you see it on an actual machine, it might look a little bit more close to you. So let's see. We have over here a program hello.c. Very simple. We just print out hello world. Like in every language, you will start out with typing out hello world. So we then send this to the GNU C compiler, GCC, very nice compiler, the most popular one, and we want to see the assembly output. As you can see, we now have two files, one hello.c, one hello.s. If I open that hello.s, as you can see, this is actually the assembly code of my program. And we have seen this is what the processor will actually do, but represented in a human readable form, even though it might not look as human readable. Anyway, what we then can do, because as I've said, the processor won't understand this. If you feed this, exactly this into the processor, it won't understand, because these are ASCII characters. We have to compile this and then assemble it to machine language. So I will do that right here. As you can see now we have an executable, so we can run the executable like that, and as you can see, all it does, it prints out hello world. Now let's open the executable and see what's inside. And as you can see, we have pretty much gibberish. So what's happening over here? You have probably expected that here we will see zeros and ones, because this is actually machine code, and we thought that when we send this program to a compiler, we will then see zeros and ones, but over here we have garbage values. Or not garbage values, but meaningless symbols. Why is that? Because, let me actually open VS Code, maybe there we will see it a little better. As you can see, I've already opened it. If I open the hello file, oops, again, just meaningless symbols, gibberish, not readable at all, neither by us nor the machine. Why is that? Simply because VS Code and Vim and NeoVim and other text editors, they are text editors. They concentrate on text. So what the editor is doing is he tries to convert the hexadecimals or the binaries to ASCII characters. The editor doesn't care about machine instructions. It doesn't look for machine instructions. It looks for ASCII characters. And that's why this will look like that. Okay? Now to actually see the machine code, we will need a sophisticated program for that. For example, hexdump, and we can then pass the hello program, and as you can see, now we have the program written as binaries, but in a hexadecimal representation. So this is still not binary, this is hex base 16. So if we actually want to have binaries, because this again is an abstraction, because we just, or not an abstraction, but it's another representation of binary numbers. So if we want from this hello program to have the binaries, we can run xxd flag b and pass the hello, and as you can see over here we have the binaries. This is our hello world program. Looks pretty intimidating, to be honest, and this really, as you can see over here, it got hello world. This really is the lowest you can get from a software perspective. So this is actually what gets fed into your CPU, like that. Alright, I guess that's enough. I think we will dive into the exercises. So again, I will go into there and I'll go into my downloads folder. We see the Rust algorithm. I've already cloned it, and then I will just open cargo run this, so I can always check. And I will open a new tab, and over here, as you can see, I can then switch back and forth. Again, over here, I will go to my downloads folder, into this source exercises, and then we can start. So as you can see, the first program we will write is sum all numbers in range. So I will open that one, sum all numbers in range. Okay, now I've actually solved all the exercises, and that's why I will sometimes look at my other monitor just to write it and be a little bit faster, because I think it doesn't really make sense if I try to solve it and you see me half of the video just thinking, you know, not really beneficial to you. And that's why I will just switch over to there as algorithms, and here I have my solutions. And by the way, all the solutions, if you clone my GitHub, will be also inside your GitHub, your folder in which you cloned my GitHub repository. So let's see. Will pass you an array of two numbers. Return the sum of those two numbers plus the sum of all the numbers between them. The lowest number will not always come first. For example, sum all should return 10, because sum of all the numbers between 1 and 4, both inclusive, is 10. So the sum from 1 to 4 is 1 plus 2 is 3 plus 3 is 6 plus 4 is 10. So, and also I suggest to you that you always take a look at the tests so that you see what is actually expected. So if we pass 1 and 4, the output should be 10. If we pass 4 and 1, the output should also be 10. If we pass 5 and 10, 45, and 10 and 5, also 45. As you can see, sometimes it's in the right order, sometimes the bigger number is first, then the slower number. So what we can do over here is, first we can sort the array like that. So then the lower number will always be first and the larger number will be second. Then what we can do is we access the first value in the array, which is in this case 1, and we put the range to the second one like that, and all we do is then sum together. And you know, in Rust, if you want to return something, you omit the semicolon, so this will be the return value. So sum just takes an iterator, for example 1, 2, 3, an array, we iterate over that and run sum, and it will just sum together all the values in the iterator. Now this is a nice syntax for ranges, so we want to have the range from, for example, 1 to 4. This will then get stored in an iterator like that, 1, 2, 3, 4, and then we just take the sum from these values. Now let's see. If I save this file, I will go back over here and I type 1 for the first exercise. And let me see. Downloads. Okay. If I run the I'll run again. 1. Okay. I will just find out what's the problem. I guess it's something in the program, because if I run cargo test, As you can see, it failed. Alright, I found the problem. So again, I'm going to toggle one, and as you can see, we have passed the tests. So we have to include that one. The range operator means from this to that, including this one. So 4 has to be included. That's why we now pass all the exercises, all the tests in the first exercise. Alright, second one, let's see, div2 arrays. And here too, div2 arrays. Alright, so compare two arrays and return a new array with any items only found in one of the two given arrays, but not both. In other words, return the symmetric difference of the two arrays. Note you can return the array with its elements in order, in any order. Okay, so order doesn't matter, that's fine. So in the test, as you can see, we pass an array or a vector with these elements. And maybe just very quickly, I know over here it says array 1, array 2. This is because I have tried to be consistent and take the names from the original exercises, but we are actually passing it vectors. And the difference between arrays and vectors in Rust is that arrays are fixed size and contiguous, and vectors are can grow and shrink, and they are stored at heap memory. That's an example. So over here you can see vector 1, vector 2, and we just want to output in a new vector the items which are not found in any of them, in both of them, I should say. So for example, pink wool is only in this, but not in that. Every other item is found in both of them. So what we can do is first make a new array or a new vector in this case, and then we can in the first array iterate over every string inside array 1, that's this one, and we can then push to new array every string. So we are pushing everything that's inside into the new array. Then the second for loop, take array 2, and if the new array contains the string, so if in this array we have pushed the values of array 1, we have pushed the values of array 1 to this new array. If now a string is found from array 2 in this new array, we have to delete that from the new array. Let index new array dot iter dot position, and we pass it x. Let's string and like that. And then we can remove the index. Now what we are doing over here in new array, we are iterating over every element. So new array now stores the value of array 1. and we want to find the position. The position returns just, for example, we have here an array, and we want the position of x if x equals to 2. So this will return 1 because it's at index 1. So in this case, we want the position of x if x equals to the string in the second array we are iterating. Because remember, we are now iterating over the new array, which stores all these values. If we find a value over here that is the same, we have to then delete it from this. So we then get a position, and then we can just call remove, and remove takes an index, and then we'll remove the value from the given index. So in this case, from new array, we remove the value which is inside index, which we have found out. And else it does not contain it, then we push to new array this string from array 2, because it is not found in the first array, so we can push it. Then in the end we can sort alphabetically, sort by, we pass it a, b, a to lowercase, and we compare b to lowercase. So what we are doing over here is we are sorting by. So this will sort, for example, a compare b, and this will just sort. So the smallest number is first and the largest number is large. And that's why we have here CMP, which stands for compare. So 5 compared to 10 will return ordering less, ordering greater, ordering equal for these. So this just compares, and what we are basically doing here is we just sort the result array, so it will be sorted alphabetically. Then all we can do is we return the new array. Like that. And now let's see, 2, and all the tests passed. I hope you get that. Alright, now third exercise, which will be seek and destroy. So I go back, seek and destroy. You will be provided with an initial array, the first argument in the destroyer function, followed by one or more arguments. Remove all elements from the initial array that are of the same value as these arguments. Note you have to use the arguments object. This is for JavaScript, don't worry about that. So let's see the tests. We have here an array 1, 2, 3, 1, 2, 3, and the arguments second, here will be the array or the vector, in that case holding i32-bit integers, and the second argument will be an array of arguments. So we have here 2 and 3. So what we have to do is we have to remove from the array all the elements we pass as arguments, so 2 and 3. So we have to remove that and that and that and that, and we will be left in the end with 1 and 1. As you can see here, we remove 2 and 3, 2, 3, 2, 3, and we will be left with 1, 5, 1. I hope that's clear. So let's get it on. Seek and destroy. Like that. That's a pretty small exercise. So for arg in args, so we are iterating over the arguments passed over here, and we can do arg retain. We pass it a closure x, which then x not equals to arg. Then we put r to web, because we have here as return type a vector which holds i32 values. So let's see, the function retains only the elements specified by the predicate. So for example, we have here a vector which holds integers 1, 2, 3, 4, and we only want to retain from this vector the elements which are even, because this is modulus. So as you can see, x, which is an integer of these, if x modulus 2 is equal to 1, that means the integer is even, so we retain it in the vector, and every other element will get deleted. So pretty simple. And again, this is just so that it's compatible with the return type. Let's save. Let's see if it's actually passing. This is exercise 3, and as you can see, all the tests are passing. Nice. So exercise number 4, wherefore so that one. Let's see. Make a function that looks through an array of objects, first argument, and returns an array of all objects that have matching name and value pairs, second argument. Each name and value pair of the source object has to be present in the object from the collection if it is to be included in the returned array. For example, if the first argument is, this is an object, first Romeo, last Montag, first Mercuito, last Null, first Tybalt, last Capulet, and the second argument is last Capulet, then you must return the third object, this one, from the array, the first argument, because it contains the name and its value that was passed on as the second argument. So let's see it on an example, because this description, I don't know. Okay, so here we have a vector which holds hash maps. Now a hash map is implemented with quadratic probably. Okay, don't worry about that. A hash map is basically a map with a key value pair. So if you're from a JavaScript background, you call this stuff objects. So for example, let me just, this might be an object name, Arpan, last name, something like that. So this is an object in JavaScript, but in Rust we call this hash map. So we create a hash map from these two, first Romeo, last Montag. So this is always the key and this is the value. Then the second element in this vector will be the second person and the last person. Now the query will be a hash map with last and cabulet. So this has to match with this one, with this line. It's exactly the same, as you can see. So what we then have to return is this hash map, a vector containing a hash map, first Tibalt, last cabulet. Okay, so let's see. Again, we have here a collection which is a vector of hash maps which has key values, key string type and as value string types, and the source which again has a hash map of type string. And we return a vector of hash maps with again key value pairs of type string. So let's see. First of all, we get the collection, that's this one over here, and we iterate over the collection. And then we filter every object inside the collection. Let's just call it object for now because we can call these objects because it's in the exercise like that. And then we take the source, that one, and we iterate over the source. That's what we passed over here. So we are iterating over this hash map, and we check all the key value pairs over here in this query match. As you can see, we have key value pairs in a tuple. This is a tuple. If object, this is one hash map from this vector we have passed as collection. If this object contains key and the key from source, that's this one, last. And we also have to check if object.get key is equal to sum the value. And then all we have to do is to collect this into a vector. Now let's see again. We get the collection. This is a vector of objects. Let's call it object for now. Collection, we iterate over it, then we filter if any object, this is an object, this is an object, this is an object. We filter the object and we take the source, that's this object over here, and we iterate over this object, and then we make sure all over here, as you can see, for example, a iter all, we pass it a closure which checks is every element inside here above or greater than 0, and this will return true. So this just makes sure, and it will return a Boolean value. So we are iterating over the search query, the source, and we make sure that the object inside here contains the key of the source. For example, in this case, last. Does this object contain last? Yes. Does this object contain last? Yes. This? Yes. And we also make sure that object.get, now get is the way to access values inside the hash map. So we get this here, map.get 1, because this is the key of the first entry in the hash map, and we will return A, because this is the value of this key. So object get key, so we pass it the key, which is in this case last, and then it has to be equal sum and the value Capulet. So for example, in this object we pass it the key, which is last, and it has to equal the value of the source, which is Capulet. Does it do that? No. We have a key last, but it doesn't have a value of Capulet. This case too. Now in this case, as you can see, object get key, we get the key from the object, or not the key, we get the value of this object with key last, and then it will return some value, which is Capulet. Then this will get collected. This will be then will be the output, first to string, first Tibalt, last Capulet. And all we do in the end is just collect this. For example, we have this over here, we have a vector, we iterate, we make some manipulations, every element times 2, and then we collect it into a new vector. So we have to do that because the return type is a vector containing hash maps of key value pairs with type string. Let's see if this passes. Exercise 4. And as you can see, we pass the test. Alright, next one. Next one will be spinal tap case. That's this one. Spinal tap case. Now over here, convert a string to spinal case. Spinal case is all lowercase words joined by dashes, basically that. So as you can see, we pass it a string. This is spinal tap, and this should be the output. Everything lowercase and separated by a hyphen. So for string manipulation, I advise you to learn regex because it's really useful. So you can import regex like that, use regex, and then we can over here, as you can see in this function, we accept a string argument and we return a string. So let's write a regex new, and this is the syntax for writing regex. See, like that, and over here we put our regex. Now the first thing is we will have to make a capture, which I will call lower, and this is a little bit unfortunate, to be honest with you, because this syntax just doesn't look right. You know, JavaScript has a much nicer syntax for captures, but it's okay, you can work with it. So this is a capture group, so we want to make sure this is for this specific case. So we have here camel case, and camel case is that the words are separated by capital letters. This is spinal tap. So in JavaScript you write all the time like that, for example function names and variables, and then we have to make it like that. And this regex is just so we are able to split between here. So what we want to do is we want to test, is it lower over here, is it starting with a lowercase letter, and the second capture group will be if so the second, excuse me again, we check over here. This is the sort of the actual regex. We check, is there a lowercase letter that is being followed by an uppercase letter. This capture group is called lower and this is called upper. Now you have to call unwrap because regex new will return a result, so you have to unwrap that. So what you then will do is we take S and we assign it to this regex and we'll replace all in S, and we replace the lower like that. String. What we have done here, as you can see, we've taken this regex, and inside this string, for example, over here, we just between this and this put a white space. That's all we do right now. If there is a lowercase letter followed by an uppercase letter, then add a white space over here. Now this may look pretty cryptic. As I've said, I'm not really satisfied with this kind of capturing groups. I think there would be much nicer syntax, but that's the way it is. And then let's actually do another regex. And we are basically shadowing this variable. White space or like that. So we are matching now for white space or underscores like that. And what we now do is we split this string over here, for example that one or that one, any string that is passed over here. Then we collect this into a bag of type string slice, or which holds string slices. We put it into iterate over this new collection, and then we map each string and put it to lower case like that, and then again we collect it inside a bag of type string. Why? Because our return type has to be a string and not string slice. These are different values. I've made a video about that, you can check that out. And then we just join with a type like that. And let me see, there is an error because I have forgotten the point. Now, of course, we are here manipulating S. So S actually has to be mutable like that. And yeah, let's see. So exercise 5. And we are passing all the tests again. So I hope you get what we've done here. We have regex. Admittedly, this looks a little bit complicated, but in reality it's not. Just don't think about that one. And all we do is we check for this case, if there is a letter lowercase which is followed by an uppercase, we put a white space between them. Then we split the string on white space or underscores. So we split, this will be a vector then, this will be a vector, this is, and so on. You know what I mean. We split it on white space or underscores. Now this will also get splitted. Why? Because we have added a white space between lower and uppercase letters. Okay. Then we collect it into a vector of string slices. This needs to be done because we have to add here a reference, and string slices are references, and yeah, and then we map every string. So this is a string, this is a string, this is a string, this is a string inside this collected vector, and we put everything to lowercase. Then we collect again and we join it, and it will then look like that. Alright, next exercise. Spinal tap case is done. Pig Latin. And again, if you didn't like regex, here we go again. So Pig Latin is a way of altering English words. The rules are as follows. If a word begins with a consonant, take the first consonant or consonant cluster, move it to the end of the word and add a to it. If a word begins with a vowel, just add way at the end. Translate the provided string to Pig Latin. Input strings are guaranteed to be English words in all lowercase. Okay, so if we pass California, this is a consonant, so what we have to do is we have to put this C at the end, and as A is a vowel, we stop here. So we put C at the end and we add A to it. So the result will be California K. And for example, paragraphs, as you can see, we start with a consonant. So we put this at the end and put an A to it. Now, as you can see, we pass here a globe. We have now two consonants before a vowel, so we put these two at the end of the word, then add A. And now, as you can see, we start with a vowel, so we just add at the end of the word way. Okay? Now let's see. Pig Latin. Again, we will do regex, because if you're dealing with string manipulation, regex just is the best out there, but this time without capture groups, so it will look a lot more pleasing. So, of course, we have to import regex first, like that. Now, what are we matching over here? We are basically just matching if the word starts with a consonant, with a vowel, sorry. We are checking if the word starts with a vowel. This means the start of the word, and this checks if it is either A or E or I or U or U. and not only one, it can be anything, one or more of these vowels. So then we will create a new string just to store inside the result string we will return. So let's see. Then if this regex matches is matched in the string we are provided, then what we will do, result push string, and we push the string, and then result push string, and we just add way to it. Because why is that? Because if this regex matches, it means that the first letters of the word are vowels. Now, if a word begins with a vowel, just add way at the end. That's what we have here. It starts with a vowel, so we just add way at the end. If this regex doesn't match, then we will do another regex, and again we have capture groups. So this is consonant, oops, consonant, here we have the rest. Like that. So what we are checking over here, if the word is starting with a consonant, then we take this capture group over here. So we are taking these consonants, and what this is checking at the end of the word, it is not, this means is not any of these one or more time. So for example in glove it's 2 times not a vowel, so we have to take this and this at the end and then add a epsilon. Then it's just the rest of the word. So the result will be, we replace inside the string, we have the rest, which will be first, then we have consonants, of course without a comma, and then we add a to it, and this will be translated to a string because our return type has to be of type string. And we just return the result at the end, like that. So again, a little bit cryptic, but that's the deal if you're dealing with regex. If at the beginning of the word we don't have one of these, one or more, this plus means one or more of these, then it matches, and we basically, this is a capture group, so we capture any consonant until we find a vowel, which will then be put at rest. So what we do is we just put rest first and then the consonant, and in the end we add a epsilon. Like that. Let me see. I think this is the last regex exercise. So as you can see, we passed the test. All right, next one. Let me actually search and replace. Perform a search and replace on the sentence using the arguments provided and return the new sentence. First argument is the sentence to perform the search and replace on. Second argument is the word that you will be replacing before. Third argument is what you will be replacing the second argument with after. Note, preserve the case of the first character in the original word when you are replacing it. For example, if you mean to replace the word book with the word dog, it should be replaced as dog. Again, the description sometimes it's really hard to understand. That's why we look at the test. So we have a function over here, myReplace, which we have to implement. We pass it a string. Let us go to the store, and we have to replace store with mall. So in the end, we have a result string. Let us go to the mall. Now again, what this description talked about is keeping uppercase. So he is sleeping on the couch. If we provide sitting, then sitting should be uppercase too, because sleeping in this case was uppercase. So instead of sleeping we have sitting, but it needs to preserve the case. Okay. Let's search and replace. And I'm sorry guys, but again, regex, because again we are manipulating strings. So I will write a regex over here. It's very simple, like that. So we check, what does that mean? In the beginning, is it a capital letter from A, B to Z, like that? So we check at the beginning of the word, is it a capital letter from A to Z? Then I will do after string. We'll just convert this from a string slice to an owned type to a string, because this will be the return value. So let's see if this regex matches before. So we check if this actually starts with an uppercase letter. So this is the before argument over here, and we check, for example, here it would be a match because the first letter is uppercase. So then we do after first to upper, and we will implement this function after a little bit. After. And what this does is basically just puts the first letter of after uppercase. Very simple, we implement it right away. Else if this regex doesn't match the before string and it matches the after, then after will be after to lower case, like that. And then we just can replace before with after, like that. Now as you can see, you cannot find function first to upper because we have to implement it. So first to upper, which just takes a string slice. Like that, and we return a string. So we have have here an iterator over this string. So as you can see, goodbye, if you put the goodbye string in chars, and then as you can see, we just iterate over every one of them. So match c.next, which will be the first letter. If it's null, we just return a new string. And if there is some letter, then this will be first. So first to uppercase, then we collect this into a string, and we add C as string, which basically just adds to the first letter the rest of the string. Again, just to show you what we've done here, we have first wrote a regex. We have first written a regex, which checks is the beginning of the word capital letter. Then we match this with before. So if this before starts with a capital letter, then we will put after to this function, which then just makes the first letter of after uppercase. If it does not match in before and it matches in after, so for example this here, in before it doesn't match, but in after we have a capital letter, then we just have to make after all to lowercase, like that. And then what we can do in the string, for example over here, we just replace store with mol, like that. So we get this. Let's see. This was search and replace, I guess. As you can see, we are passing all the exercises. Alright, next one will be DNA pairing. Pairs of DNA strands consist of nucleobase pairs. Base pairs are represented by the characters AT and CG, which form building blocks of the DNA double helix. The DNA strand is missing the pairing element. Write a function to match the missing base pairs for the provided DNA strand. For each character in the provided string, find the base pair character. Return the result as a 2D array. For example, for the input GCG, return GC, GC, CG, GC. The character in this pair are paired up in an array, and all the arrays are grouped into one encapsulating array. So, sounds very complicated, it is not. So, we get as input over here per element a string, which are low uppercase letters A, T, C, G, A, and every single one of them has a pair. So A has a pair of T, T has a pair of A, C has a pair of G, G has a pair of C, and A has a pair of T. And in the exercise I've already given you this function, so you don't have to write that. And yeah, all we have basically to do is just find for each of this letter the right pair. Now I will make a variable pairs, which is just an empty vector. This will then get returned over here. As you can see, we are returning a vector which holds an array of 2 characters. A vector with arrays inside, and each array holds 2 characters. Alright, Then for C in s.chars, that's what we did in the previous exercise too. We iterate from the string, provided string over here, we iterate over every character. So pairs, the empty array, we push match base pair and as argument C, and then we just return pairs. So what's happening here? Pairs is an empty vector. We push to it the result or the return value of this function match base pair, which we call with an argument of each character in this S string. So for example, in this case, in the first loop, it will call it with A. So A gets passed inside here, and this will be A. Then C, the argument will be matched. In this case, it's A. So if it's A, then it will return A T. That will be the return type. And we are just pushing that to vector. And this will go on and on. For example, the second one is T. We pass T. T over here. C gets matched with T. Then we return that and we push that to the vector. And in the end, we have a vector of the pairs. So let's see. DNA pairing is okay. All right. We have some progress over here. So missing letters. Letters. Find the missing letter in the passed letter range and return it. If all letters are present in the range, return undefined. Okay, as you can see, we have the function fear not letter, takes a string input and returns option char. So we pass it A, B, C, E. What is missing? Of course, D is missing. We pass it A, B, C, D, E. This and missing will be I. So from a range of letters, we have to find out if there is a letter missing. So let's first create a variable current for code. And this, again, we will iterate over the characters of the string. So this is an iterator. Let me show you the function again. This will put a string into an iterator, so we can then go to them. So if we call char next, we will get the first character. If we call again next, we will get the second, or you can do it in a for loop. So this next will be called implicitly. So let's see. s.chars.next, that means we get the first letter. And this will be our current char code. Then I will do another missing one, and this will be none. So for now we loop in this s.chars, and for each character in this s, if C as U8, because we are here dealing with bytes, if C as U8 is the same value as current char code, then current char code plus equals 1. Increment by 1. Else missing will be some, and the current char code as char. We here typecast it back to a char because we want a char output and not a byte. Then we can break because we found the missing letter. Then we just return missing. And of course this has to be in sum because we are returning an option, because it might also be that there is no missing letter, and that means we return none, which is the equivalent of null in JavaScript, but a lot safer. And yeah, again, what have we done? We get an input, for example, ABCE. We store the byte of the current of the first letter as the current char code in this variable. Then we iterate over this. So the first one is this, and this is represented in bytes. So if C as U8, because bytes, is equal to current char code, then current char code plus 1. Okay, that's the case because we have here the same letter, A and A. Then again, we have incremented by 1. So then again, the second one will be B. Now we will check B. Again, it matches plus 1. Then we go plus 1. And then C. Now again, C then matches again. Why? Because B plus 1, when we look at it at the byte level, plus 1 will equal to C. So the next one is C, so it matches, so we will increment by 1. Now, the problem over here is now we are at C, C equals now E. So C equals E, which has another code than our current char code, because C plus 1 will equal to D. So these are not the same, so we know the missing letter will be D. Alright. Let's see, missing letters. And this works. Okay, next one, missing letters, sorted union. Write a function that takes 2 or more arrays and returns a new array of unique values in the order of the original provided arrays. In other words, all values present from all arrays should be included in their original order, but with no duplicates in the final array. The unique numbers should be sorted by their original order, but the final array should not be sorted in numerical order. Alright, let's see the test. So we have here a function, unite unique, which takes as input a vector of vectors, which hold I32. So we pass it a vector 132, vector 5214, and we pass it another vector 2 and 8, and this is all inside one big vector. As we've written over here, vector contains I32 integer values. What we then have to do is just, we have to take from these only the unions. So for example, we have 1, we take it, 3, we take it, 2, we take it, 5, we take it, 2, it's already there, so we don't take it, 1, already there, 4, not there, so we take it, 2, there, 1, there. So in the end we have this. Alright, let me see how I solve this. sorted union. Let's see. We first do array, which holds a vector of i32 values, and we put the array into an iter, and then flatten the array and collect. So what we've done, as you can see, we have here a vector of i32 integers. We have flattened that. As you can see, here we have a vector of 2 vectors inside. We flatten it, and then we have 1 vector, like that. Then again, I will do a variable just for the result. This will be an empty vector for now. So for number in array, in this array, we iterate over every number, and this is now just one array with some numbers in it. If the result, this empty vector, contains number, if it does not, if it does not contain the number, we just push it. That's all there is to it. And in the end, we just return the result array. That's it. As you can see, we have flattened this array, and then we just iterate over it, and we check if the result array contains a number. If it doesn't, we push it, and we return the vector. Let's see. Sorted union is number 10, and all the tests are all the tests are passing. All right, next one. I think we are at the half time. Sorted union. Now we have convert HTML entities. Now this would be a nice thing for a library, for example. So convert the characters ampersand, less than, bigger than, double quote, and apostrophe in a string to their corresponding HTML entities. Some characters and the corresponding HTML entities. Okay, so here something is missing. I will fix that. So for example, in HTML, these symbols get represented a little bit differently. So if we pass this string over here to convert HTML, then we should return this. So this is how it's represented, this symbol in HTML. Or for example, less than is represented like this, ampersand LT for less than and semicolon. Or for example, greater than, ampersand greater than, semicolon. Like that. Alright, now what we can do, probably first of all, I will make const entities, and this is a nice opportunity to use a const because these things don't change, so you can make them constant. This holds 2 string slices and 5 values, this array. So we have over here ampersand, and then over here the HTML code. And you know what, I will just copy that because it doesn't make sense that you look at me just writing this stuff. So you could also have used a hash map, but I thought I will try it in this exercise with a array of tuples. It's also possible. There are many possibilities always. So let's see, we make a result variable which takes a string from S. Now, as you can see, this string slice, we will convert it to string owned type because the return type will be string. Then we iterate over entities. So we iterate over the entities array. Notice that we have now two values because every element in this array holds a tuple of a character and an entity. So let's see. Result equals replace C with E. Then we can return the result. What we are doing over here, we get passed a string, we first convert it, and then we iterate over entities. Now each element in this array has a tuple. One is the character and the other one is the HTML entity, represented by C and E over here. Now in result, which is this string over here, we replace this, for example this with the entity. That's all this does. And then we return that. Let me see. Convert HTML entities is 11. Okay, and all the tests passed. Next one, HTML entities. That's this one. Okay, Fibonacci numbers. That. Alright. Given a positive integer num, return the sum of all odd Fibonacci numbers that are less than or equal to num. The first two numbers in the Fibonacci sequence are 0 and 1. Every additional number in the sequence is the sum of the two previous numbers. The first 7 numbers of the Fibonacci sequence are 0, 1, 1, 2, 3, 5, and 8. As you can see, 0 and 1 is 1, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, and so on. For example, some fibs 10 should return 10 because all odd Fibonacci numbers less than or equal to 10 are 1, 1, 3, and 5. So this is the sum of the odd Fibonacci numbers. Alright, looks pretty complicated, but it's not that big of a deal. So we create a variable, two variables, 0 and 1. We assume that our current variable is 1 and the previous one is 0. Then we create one for the sum, which we initialize to 0, and then we iterate over nothing. We don't iterate over anything. We just check if current is smaller than or equal to number. So is current smaller than or equal to number? This case, yes. We pass it, for example, let's take this one, it's simpler, 4. So num is 4. Now we check, is current less than or equal to 4? Current in this case is 1. So 1 is equal, 1 is less than 4, so we loop. So if current and modulus 2 is 1, then sum plus current. So this is just a check, is the current integer, is it divisible by 2? If it's not, in this case, it's odd. So we add this to the sum. Then what we have to do is next will be pref plus current. So the next number over here, as you can see, will be previous 0 plus current 1. This is our next number. Then we have to reset previous. This will be the current, and the current will be the next number. Then we just return the sum. So as you can see, we then have the next one, previous plus current, 0 plus 1 will be 1. Then we set the current one to the previous. So previous was 0 and current was 1. So we set current to be previous. So this will be previous and next will be current. So this will be current. And then it will loop all the way until it reaches, until current is equal to number. Okay, let's save that. Let's see. Let me actually run it again. Sum of Fibonacci 12 plus 12. As you can see, we are passing all tests. Alright, now let's see some all primes. Alright, sum all primes. This one. A prime number is a whole number greater than 1 with exactly 2 divisors, 1 and itself. For example, 2 is a prime number because it is only divisible by 1 and 2. In contrast, 4 is not a prime number since it is divisible by 1, 2 and 4. We write sum prime so it returns the sum of all prime numbers that are less than or equal to num. Again, we have a function which expects an argument of num, type I64. So as you can see, we pass it 10. Now we have to check from a range from 2 to and including num. We filter, it's the number is prime, and then we just have to sum. Now of course there is no function called is prime, so we will have to implement that. So let me write the function is prime, also expects a number of type I64 or integer, and it will just return a bool, which is either true or false. Again, we iterate over the range from 2 and including n as f64. It has to be float. Then we take the square root of that as I64, because remember we are dealing with I64 numbers, but we have to convert it for the square root function. As you can see, this has to be of type f64, floating point number. And then we check all, and we check the integer, is it divisible, and if it is a prime. So again, let's see, we pass this 10. Then we have to check, returns the sum of all prime numbers that are less than or equal to num. So then we have to check all the values for example we pass here 10, so we have now to find all the prime numbers from 2 to 10. Of course 1 is not a prime number, so we don't have to check for 1 over here. We start at 2. And then we just sum all the prime numbers. So that's what we are doing. We are checking from 2 and including num, which in this case is 10. So we have an iterator. As remember the syntax, so we'll just put this into an iterator. 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's what this is doing. Then we filter and we check every number, is it prime or not. So this involves a function call. So we go over here. So every number from here gets passed over here and will be checked. And to check if it is prime, we just, for example, 2 to 2 will just output 2, and then we take the square root of 2 and we check basically if the given number n is not evenly divisible by all numbers from 2 to the square root of the given number. We check that, for example, 8. We then check from 2, 3, 4, 5, 6, 7, 8, which will get passed here. As you can see, from 2 to 8. We take the square root of that and we check every value, is it divisible by I, by itself. Okay, that's all this function really does. Alright, let's see. Sum all primes is number 13. And the tests get passed. Now, smallest common multiple. Okay, so find the smallest common multiple of the provided parameters that can be evenly divided by both as well as by all sequential numbers in the range between these parameters. The range will be an array of two numbers that will not necessarily be in numerical order. For example, if given 1 and 3, find the smallest common multiple of both 1 and 3 that is also evenly divisible by all numbers between 1 and 3. The answer here would be 6. Okay, so again we have here a range. The smallest common multiple of 1 and 2 and 3 and 4 and 5 is, in this case, 16. So, first of all, as you can see, sometimes the larger number is passed first and then the smaller number. So, as we did in the beginning, we sort the array. That's step 1. Then, let's start and end. We declare two variables, array 0 and array 1. Basically this and this value, this will be stored in start, and this will stored in end. Not really that necessary, but just for readability of the code. Then lowest common multiple or smallest common multiple will be a range from start to and including end, and then we fold. We'll come to that in a moment. Start, we have an accumulator number, and we do that accumulator times number divided by this function, which I will come to in a moment. Then we just return LCM, the lowest common multiple. Okay, now what is the fold function? If you come from JavaScript, you know the reduce function, so it's basically the same. It's when you have an input of various integers or any other type, and you want to fold them up to only one value. For example, here we have an array, we iterate over it, we fold, we start at 0, this is the accumulator, this is x, which can be 1, 2, 3, the iteration, and in every iteration we add x, for example in the first one 1, to the accumulator, then 2, and then 3, and the sum then will be 6. Alright, and then what we are here doing, from the range of start to end, multiplying each number in the range by the accumulator value and dividing the result by the greatest common divisor of the accumulator value. So we have also a function to implement, greatest common divisor, which expects 2 i32 values, and it returns 1 i32 value. We match b, and if b is 0, then return a, else we recursively call this function, passing b as argument a, and passing b the result of a modulus b. So, and of course we have to make this mutable because we are sorting over here, so this has to be mutable. Alright, now this finds the common divisor, or the greatest common divisor of 2 ints. And this is pretty clever because, for example, if you have here 16 and here 4, then it will check b, which is 4. So b is not 0, it is 4, so this will get executed. So we pass 4 to a, and here we pass, a was 16, 16 modulus 4 will be 16. So what we have actually done is then we have switched the values. So this is now 4 and this is 16. At the beginning it was this 16 and this was 4. Now we check again. B is now 16. Again we check, is B 0? No. We pass 16 over here, and this 16, excuse me, B is 4, so we pass here 4, and this will be 16 modulus 4. 16 modulus 4 will be 0, because 4 times 4 is 16, so there is no remainder. So B will be 0. Then 0 is matched because B is 0, so we return A. So the greatest common divisor of 16 and 4 is in fact 4. Pretty clever function, solved by recursion. And then over here we just check the greatest common divisor of the accumulator and the current number in the range. We divide that by the accumulator times the current number. So we will get the smallest common multiple. Right, let's see smallest common multiple. Done. Alright. Now drop it. Given the array R, iterate through and remove each element starting from the first element, the 0 index, until the function func returns true when the iterated element is passed through it. Then return the rest of the array once the condition is satisfied. Otherwise, R should be returned as an empty array. So let me open drop it over here. So as you can see, we pass here an array, a vector 1, 2, 3, 4, which has integers inside, and we pass here a closure, which is basically a function. And as you can see, the closure is called filter, and here it's defined. So it's a function which as the parameter will accept a reference of a i32 value, and it will return a bool. So what we want to do over here is we call this function drop elements, pass this array 1, 2, 3, 4, and we pass this closure. We want to drop all the values in which this closure returns true. So for example, 1 will be inside n. Is 1 greater than or equal to 3? Not. So it will get dropped. Is 2 greater than or equal to 3? Not. Dropped. 3 is equal to 3. It stays. 4 is greater than 3, so it stays. So let's see. We'll firstly iterate over array over here that will get passed, and this time we iterate and we enumerate like that. Let me show you that. Enumerate basically takes an array, and what it does, it enumerates the array. So this will have 1 is A, 2 is B, 3 is C. This will get stored in a tuple. So if we put that in an iterator and do next, as you can see, we then have a tuple 0, because it's 0 indexed, of course, will be A, 1 will be B, C will be 2 in a tuple. So that's why we can dereference it like that. We have the index and we have the value. All right. Then we check if filter, that's this closure, we are passing value. So if this returns true, you don't have to write like that, it's implicit. Filter returns true, then return the array from index I to the end of the array, and we put that into a vector. Then in the end we just return an empty vector if nothing was actually returned over here. So if this filter is always false, then we just return an empty vector like that. As you can see, we just took this vector over here, we have enumerated, so we get the index and the values, and then if this filter, the value, for example 1, passes over here, so we are putting the value to this filter, so n will then get the value, for example 1, then 2, then 3, then 4. If it returns true, then return this array, but only from the index I, which was found true, to the end of the array. Okay, let's see. This was drop it 15, and we passed all the tests. Alright, not much left. Let's see, Steamroller. So Steamroller was a little pain in the ass, but let's see. What we basically have to do here is flatten a vector or an array of arrays. So as you can see, I have implemented this as an enum, and you can use this code. So this enum basically says it can either have two values, either inside the vector is a number which holds I32, or is an array which holds vector and a value. The value, as you can notice, this is recursive. And let's see, Steamroll array, we accept an array or a reference of an array as input, and we return a vector. Now, as you can see, we have inside here a number 1, and then we have an array which holds number 2, and then we have an array which holds number 3, and another array which holds an array which holds number 4. What we want to have in the end is just one single flattened vector. So actually this exercise, not that necessary you have in Rust the flatten function, so this will do it automatically for you. You don't have to worry about that, but just for completion's sake. So we have a variable result which will store the vector we will return. So for value in array, we iterate over the elements in this array. We want to have a match. So if it holds value number, that's this enum, then we take this number n and we push it to the result. And of course, over here, we have to dereference it because I32 over here is a reference. So we have to dereference it. This holds reference of I32 values. But if its value is an array, then we have a subarray over here. Then we can result extend Steamroll array. As you can see, we are using recursion again, and in the end you just return result. Now this extend method, which is, for example, we put this string ABC in an iter, and excuse me, we have this string ABC, we extend it with an iterator, and as you can see in the end we get ABC DEF. So extends a collection with the contents of an iterator. That's exactly what we are doing here. We are extending result with the return value of this. We're passing this function, as you can see, recursion, this subarray, which then will do the same thing, and in the end we will get result. So let me see, what was that? Steamroller 16, and we passed the test. Okay, then binary agents. Return an English translated sentence of the past binary string. The binary string will be space separated. Okay. So let's see. Again, first thing, I create a variable which will hold the finite string we will return over here. Then we iterate for byte in s.split. So we have this string which get passed as s, and we split it over here. So this will be an element of the array, this will be an element, this will be an element, and so on. Then we can map x. And then there is a function, I didn't know it, I've read it in the documentation, from string radix, and we can pass x over here and 2 for binary number, and we can then unwrap, because this, as you can see, will return a result. So we have to unwrap, and yeah, converts a string slice in a given base to an integer. Right. So this is base 2 binary, and it will then convert it to a string slice, to an integer. I'm sorry, to an integer, to an U8 byte integer, which I guess will be an ASCII character. And then all we do is result.push, and we push the byte as character. Now we push this ASCII character as char, of course, and we return the result. That's all it does. So again, we took s as input, we have splitted it, so every byte, I guess it's a byte, 1, 2, 3, 4, 6, 8, 8. So every byte over here gets splitted, and every byte is in its own, has its own element in a vector. Then we map over it, so x represents these bytes, and from string radix. So we want, this is in binary, base 2, this string, we want to convert it to an U8 byte, which then can be represented as ASCII, because here we are then converting it to char, which converts the byte to a char. And we just then push the ASCII character to the result string, like that. As you can see, Armed Bonfire is fun, and I love Free Code Camp is the message. Okay, binary agents 17 passed, that's fine. Okay, next one, everything be true. Check if the predicate second argument is truthy on all elements of a collection first argument. In other words, you're given an array collection of objects. The predicate pre will be an object property, and you need to return true if its value is truthy. Otherwise, return false. In JavaScript, truthy values are values that translate to true when evaluated in a Boolean context. Yeah, this is very specific to JavaScript. Remember, you can access object properties through either dot notation or square bracket notation. Also very JavaScript specific. Enum to hold. Okay, this is from me. Let's see, everything be true. So we have here over our tests. We have person 1 as P1, and every person has a name, a role, a role and is bot. So this is Quincy, founder. This is Naomi, doesn't have a role and false, is not a bot. And this is Camperbot, the role is bot and is bot is true. Then we put these into a collection, and then we check if, for example, we pass here is bot. Is this true or false? And as you can see, we have false values over here, so it will be false. It's only true if all of them have true in here at is bot. So basically what we have over here already is a type. We have type person and we have type Pokemon, because here we have also Pokemons. Let me see over here, string from Pikachu, number 25, code 3. And we are basically checking the same thing. So can either be person or Pokemon. And as you can see, person, every person has a name, which is of type string, a role, which is of type string, and is bot, which is of type bool. A Pokemon can also have a name of type string, a number of type i32, and code i32. Basically the number of Pokemons you have caught. Now we have to implement type over here, and we will do that by just actually implementing the methods. So we have a method name, which returns a string slice, and all it does, it matches self, so the object on which the method is called. And if it's type person, then we can return the person.name, else we will panic. Not valid type, as you can see. Then we have a method for role, again self. We have string over here, and we match self again. Oops. And again, if it's type person, then we return person dot role, and else we panic. Else we panic. Not valid type. Or let's do it like that. Not a valid type. Not a valid type. Like that. Right. Then one is bot. Again, take self, a reference to it. This will return a bool. Then we match self. If the type is person, then we just return person dot is bot. Else again we panic, and I just can copy that over here so I don't have to type it once again. And F and number, this is related to Pokemons, which we have here self. This will return a i32 value, and we match self with of type Pokemon. Pokemon number will be returned, else we'll just panic. And the last one, bot self, and I32, we match self by Pokemon caught. Else again, we just copy that one over here, so like that. Alright, so we have our methods. So these methods can then be called on any type that implements type. Okay, and now we have, of course, to write this in the function over here, truth check. So in collection, as you remember, collection is just a vector of various persons or Pokemons. So in the collection, we iterate over all the elements, and all of the persons or Pokemons match the name should be name. This is the method we call on this person. The method name is not equal to an empty string, like that. Or if role is not an empty string, or is both is not equal to false, and or is number not equal to number 0, or code like that. If this panic new file name found for free, like that. So this exercise is a little bit JavaScript specific, so we have here to emulate that, and we have to basically say, because in JavaScript, for example, an empty string is falsy. This is falsy. False is also falsy. 0, 0 is falsy. So we emulate that, and we are just checking if all of them in the collection, as you can see, this is the collection of persons. If we iterate over all of them and call the all, I think I've shown you already, this just checks if all the conditions are met, if all of them are true. So in this case, it will just return a boolean. If all of them are true, so name is not equal to an empty string, that means we don't have falsy values inside our collection. This is just basically emulating how JavaScript behaves. Okay, everything be true. We are passing. Okay. Then arguments optional. So create a function that sums two arguments together. If only one argument is provided, then return a function that expects one argument and returns the sum. For example, add together 2, 3 should return 5, and add together 2 should return a function. Calling this return function with a single argument will then return the sum. So This is basically called currying. So you can, for example, call curry 5, and this will return a function. And then you can call this function with another parameter, and then it will add these two together. So this is something I don't use quite a lot, but we write the curly closure. As you can see, this will then get returned, and this function over here returns I32. Over here, what we do is just we add A and B like that. So again, if we call this function, we pass it two parameters, they will get added together. If we call curry and pass it one integer, then this will return a function, which is this function. So 5 will be stored in this function, which is x. Then you pass it, or sorry, a, of course. This is a. 5 will be a. And then when you call this function, so as you can see, we call curry, we store the result of curry, which is a function, in a variable add5. And when we call add5 with another parameter 7, so 7 will then get put into this, so it will then return the sum of these two values. Let's see. Arguments optional, and we passed. All right. I think two are left. Make a person. So this is pretty simple. I guess even more simple than the JavaScript. Fill in the object constructor with the following methods below. So we don't call it object constructor, but this is JavaScript language. Get first name, get last name, get full name, get first name, get set first name, set last name, set full name. Run the test to see the expected output for each method. So what we do here is we just create a person, Bob Ross. As you can see over here, struct person, and then we can call the method on it, and we have a return value. For example, we call the method get first name, and it will return Bob. So every person over here has two fields. First name is a string, and last name is also a string. Then all we have to do is just implement these methods. So create, what this will do is just it will create a new person. So it's a first name to string, last name to string, like that. So if we call person.create and pass it two arguments, first name and last name, it just creates one person for us. This is also what is called, I guess, constructor, right? So get first name, I will return itself dot first name, because from the person we just, from the object we just return the field first name. Same thing with last name, self dot last name, and full name. Here we will return a formatted string because we will push them together like that. So return self first name and self last name, like that. set first name, which is type first name, set first name is equal to first name dot to string, the value that gets passed over here. Same thing, last name self dot last name equals last name, this value dot to string, and set full name is set self first name equals first name dot to string, and self dot last name is equal last name dot to string, like that. And as you can see, for example, the last three ones, we create a person, we set first name of Bob to Haskell, and then the person Bob, if we call get full name, we get Haskell Ross, because we have changed Bob to Haskell. Alright, and the other tests are basically the same logic. So let's see, 20. Alright, alt spacing, and we are at the last exercise. Let's see. According to Kepler's third law, the orbital period T of 2-point masses orbiting each other in a circular or elliptic orbit is T equals the square root of pi 2 times pi, excuse me, once again, T, the orbital period T, is equal 2 times pi of the square root of a to the power of 3 divided by the GM, the standard gravitational parameter. So A is the orbit's semi-major axis, GM is the standard gravitational parameter, G is the gravitational constant, and M is the mass of the more massive body. Return a new array that transforms the element's average altitude into their orbital periods in seconds. The array will contain objects in the format name, average alt. The values should be rounded to the nearest whole number. The body being orbited is Earth. The radius of the Earth is this much kilometers, and the GM value of Earth is that much kilometers. So let's see. We have made here a struct satellite. Each satellite has a name and an average altitude. Then we have the function orbital period, which computes the orbital period of a satellite or a planet, basically, and returns that in a vector which holds a tuple. So as you can see, we have, for example, Sputnik, which is a satellite. Its name is Sputnik, and its average alt is this value. And here we have 3 satellites, and in the result we have a vector of 3 tuples which holds the average altitude. So this is just mathematically a little bit difficult, but you can basically just write down what is actually given. So we have GM, which is of type F64, and by the way, if you have a constant, you always have to annotate the type. So the GM is actually this value over here. So I take that value and pass it over there. So let's see. Then again, const Earth radius again, this is F64 floating point, and again, see, I can take this and paste it over here. So we already have two values. Now we can iterate over this array, and that's the array over here. So we have satellite, and we pass this function an array of satellites. So, and we map over each satellite, and let's see, and we basically compute the Earth by adding the Earth radius and the satellite average altitude, like that. And the orbital period is computed by this formula. So we can just write it like that. But before I do that, I want to import a constant 64 points, and pi or p is in there. So as you can see, we can then just basically translate this formula into code, which isn't that difficult to do. So we have two floating point number times pi times Earth to the power of 3 divided by the GM, by this value, and then we take the square root, and as you can see, I'm just following that, 2 times pi, then as this a to the power of 3 divided by GM, and then we have to take the square root of that. And of course, we will round the number and as I32. And all we then do is just we return set name.clone. We have to clone the name because it's a string, as you can see. And the orbital period we have here computed. And then all we do is we collect that into the vector like that. So this is just mathematically a little bit confusing, but you can really just put the numbers in here and then translate this formula into code, which isn't that difficult to do. Alright, let's see if it's passing. This is the last one. Alright, and it's passing, and I'll quit out of the program by typing 0. And again, if I do cargo run, and over here I can just type all, and as you can see, 82 tests passed. So we have passed all the tests. And if you have made it this far, congratulations, and I hope to see you in the next video. Have a good time.